So, welcome beautiful humans to the second session of the day. Today in our first session we already talked about actors and the actor model, and Vagif Abilov now will talk to you about reliable messaging in the world of actors. Have fun.
Good morning. Thank you for coming to my talk. Hannes, who went to the previous session about DDD and actors by Hannes? Okay, good. So we both share faith in the actor model with Hannes, but we didn't agree about like what we're going to send, and I think it made actually a pretty good match. Like our sessions may complement each other because we both work with the actor model. I also think that the actor model is OP done right. I spent something like 15, maybe almost 20 years doing OP in first C++ and C#. I think if I was to write OP programs now, I would definitely do it using actors. So my name is Vagif. I work for a Norwegian consultancy company, Miles. I work mostly with F# and C#. Last 5-6 years it was plain F#. And Hannes said it was his first talk in Berlin. I talked a few times in Potsdam. I don't know if Potsdam counts as Berlin or not. It does? Yeah, well, yeah, okay. But then this my first talk is in the central Berlin. We can say that. So the system, all my talks say sort of retrospective of what we dealing with with our systems, and our product. I work in a project for Norwegian Broadcasting Corporation. It's a Norwegian version of BBC, you can say. So our product is what we do. We offer TV programs, radio programs, news, weather forecast to general public, and our small group is responsibility to take care of distribution engine, media file distribution engine. So anything that is uploaded to the cloud goes through the engine. So distribution engine, which has at large this architecture. So it's very, very sort of at large diagram, but we have durable queues where we receive commands about what needs to be done. Command adapters, everything which is on a brown section, it's our Akka cluster. And in the end, when we're done with our job, we send events also to durable queues, and this is what's happening inside. We transform commands into some units of works and send to the transport layer, which uploads files to two actually origins, two CDNs. This is for redundancy reasons. So our technical stack is close to what Hannes presented earlier this morning. It's just that we don't use C# as the main programming language. We use F#, actor model, Akka.NET. We use RabbitMQ and Azure Service Bus as durable queues, and various database backends, like both SQL and NoSQL. All my talk today, it's not really language dependent or platform dependent, and also some of the conclusions I will make, I think they can also be applied to your system if you don't use actors actually. So don't think that you need to know something about our internals or about something about F#. I think it's very good match, the actor model and functional programming and languages like F#, but it's totally your choice what you're going to implement your system in. So this talk is a sort of retrospective about changes in our approach to message handling guarantee. Because actors, they're all about messages, about sending and receiving messages. And then, okay, so what kind of guarantee they have? So how to make sure that messages don't get lost? And if you get lost, I mean, what do we do? So we must think about it. And I decided to show the changes of the approaches we made, because it helps often not to show just a final solution, because you may lack reasoning behind that. And sometimes a good way to present reasoning is to show stories of failures, like how you initially build the system, what you had to change. And I also would like to stress out that you don't need to agree with me about some of the reasons, like, for example, like I'll show you first approach, and this is something which was okay with several people I discussed. I even discussed briefly with Greg Young, who stands behind event sourcing. I said, oh, that's perfectly okay, but eventually we decided to change that approach. So it's for you to think about what is for you, what works for you. So how do we provide message handling guarantee? Because we need in our system to have guaranteed behavior, the guaranteed output. So first of all, let's have a look at semantics to deliver guarantees. You have at most once delivery, and it may sound first as something that in a serious system should not be used until you think about that every in-memory system that runs in memory, of course it has at most once guarantee. Because if you push the button and your machine is turned off and then you switch it on, everything is gone. And then you have at least once delivery, where there is a in this case, you need some sort of idempotency in your system that if a message is not handled properly, if you didn't acknowledge it, then you will get it again. And then you have to face the consequences of that, whether it's good or bad. Then there is exactly once delivery. And so it's a very strict delivery guarantee. And in database world, you can compare it with this ACID properties of database transactions. And if you think about like two-phase commit and database transactions, it's kind of complicated protocol. But in some cases, you need that. And I guess the whole talk can be devoted to why it's a bad idea to implement unless you really have very good reasons for that. Because it's complicated, it has high associated costs. Sometimes you need to do that. So what do you think the actor models, like popular actor models framework, like Akka, like Orleans, what do they have as sort of default behavior? Who think that they use at most once delivery by default? Okay, a few hands. Who think that they have at least once delivery? More hands. Who think that they have exactly once delivery? Yes, one hand. Okay, so in major actor system which are available, they use by default at most once delivery. And they have it for good reasons. Hannes had a talk, in the previous talk he showed that like on his tiny PC he could send about 5 million messages per second. And on a more powerful machine, you can send something like 50 million messages a second. So actors are very cheap to create. Actors are very responsive, very sort of quick. And so why should they offer as default at least one messenger? Because that will require some sort of confirmation, serialization of messages. So they don't do it. They don't offer it by default. This is something you need to opt for inside, if you can. So there are very good reasons. Also, actor model. If you look at check the motivations behind the actor model presented by those who created the actor model, Carl Hewitt, for example, and other people who came with ideas of actors 50 years ago. they explained it that they were thinking about physical processes behind actors. So actors try to reflect a real world. And the real world actually managed to work quite efficiently without these formalities of like at least once message delivery guarantee. But can we run a reliable system with at most once message delivery? So then, okay, so we know that we have akka.net, we have Orleans, and then, so if we turn off the machine, everything will be gone. So how can we run the whole system? So we need to provide some sort of guarantee. So when messages enter this box, they will be taken care of, even if the whole system crashes. So this is how our message queue configuration looks. And actually, this part hasn't changed for 5-6 years. So I will guide you through some series of changes to message deliveries. But this just stayed as it is. So this is input of our system. We're using RabbitMQ. And then it's a lot you can declare on Rabbit. You can specify, for example, TTL. It's time to leave. If a message leaves for a certain amount of time, for example, in retries queue, time to leave is 5 minutes. So in 5 minutes, message will be dead. And then it uses configuration DLX, dead letter exchange, to be sent back to the main queue. You have errors, usually when messages enter errors queue. In 1 hour, they will be processed back to the main queue. If a message has some unrecoverable failure, so like wrong, bad message, then it will be sent to reject queue. But then the billion-dollar question then, okay, what is the criteria to acknowledge message as done, as processed, completed? So our first version, if I use quotes from rock songs, then it will be from Chris de Burgh, don't pay the ferryman until he gets you to the other side. So it was a relatively simple concept, just wait acknowledging anything until you're done. So it will look something like this. So you have message queue, and then it goes through a chain of actors. Each actor does its job, and then finally the last actor sends confirmation, which is ACK, if message is successfully processed. So it looks like a transactional guard, although it's not really transactional semantic, because the RabbitMQ doesn't support some database transactional in a database sense, but it's just at least once delivered. It means that if we NAC message somewhere, if we don't acknowledge, or if acknowledge that it failed, then message will be redelivered. Which means that actually every intermediate actor in chain had a power of NACking a message. Okay, something went wrong, NAC it. Something went wrong, NAC it. And only the last actor in chain, it could really say, okay, I commit it, I acknowledge it, I ACK it. So if you think about patterns, like messaging patterns, so I think the closest pattern that comes in mind is return address pattern. So we had to deliver all messages in envelopes. An envelope contained the acknowledgement ID as kind of return address. So after we're done with message, we need to sort of send, to reply to the original queue. Okay, we are done with processing. So we had this is message envelope. We have a message payload, and this is ACK ID. So we sort of ACK it in the end. So it worked. It sort of worked. So what drawbacks did we find after working with the systems? Well, the first one is not really big one. It's just that you can't really send sort of naked raw domain messages. You have to always deal with envelopes, and the envelopes, they contain this acknowledgement ID. But it's okay. Then what was less convenient, and that we could no longer think about actors as small independent modules of processing, because each actor was involved in this chain of acknowledgement or disacknowledgement. So last actor in chain is responsible for act. Every actor, other actor could use NAC. Last actor also could use NAC. And actors in the middle, they could not issue ACK because it was responsibility of the last actor. So actors needed to know its place in the processing chain. And actually it happened to us a few times that the processing chain changed. So previous last actor was no longer a last actor, but then we didn't change the implementation, and then this acknowledgement went from at the wrong stage. What was more serious is that operations could be long-running, and queues could be configured with time-to-live policies. And this was our real case because we uploading large files. So if it's a long movie, then a file can be several gigabytes. Actually, Norwegian television offers some really crazy long, like typical Norwegian style programs where like just place somewhere camera and then camera just shoots what's happening there for hours, and you can have like 24 hours stream of something. And I think about that you need to upload these files, and then queues should wait until you're done. So it hints you about some wrong pattern here. So why? Because are you acknowledging message delivery, or do you really think about as a transaction? So you acknowledge the completeness of the whole operation. Also, message processing workflow can contain forks, and that was also our case. That we had a program, a TV program, which consists of multiple files of different qualities. So we actually fork messages, and then okay, who should then act this queue? So and then this also brings us to the question: how long should a postman wait? So is it really right that postman comes to you with a letter, and then instead of like signing, if it's a recommended registered letter, you say, okay, let me write an answer, or wait until I'm done with the whole thing which is in this letter? So again, if the more I think about the actor model, I think when I started working with actors, I treated them quite sort of formally. There's an alternative to OP, but I don't really think real world. Like every time I modeled with actors something that didn't really reflect real world, eventually I started thinking, okay, I should think more about a reflection of real world. So this is Postman thing. It was bothering me. Okay, we let Postman wait. So in version 2, it was kind of tactical change. I wouldn't say that really big change. We started using durable queues as like persistent bookmarks. So what we did is we split these operations. Also, it solved our issues with forks. When we fork operation, then we have multiple operations that are a result of a big operations. We could do it like that. Okay, we have a TV program, we split files, and then we have multiple queue requests here. So, and we use basically these durable queues in the middle, like at some intermediate stages. And then on each stage, we have at least once. So while it really improved this problem with long transactions, but it was not a principal improvement. And then we still had to put all messages into these envelopes with acknowledgement IDs. And then an actor system really got partitioned. It looked like we had multiple actor systems. Then still, some units of work they could still be long-running and exceed this time-to-live values that we configured for message queues. So it didn't really solve the problem of a postman waiting for an action to be completed. So we thought that, okay, we should think about something else. So our version 3 was, it was the shortest in time version of our system because we soon realized that it was a wrong path. We tried to use, okay, we need to deal with at least one delivery, but actually there is some akka.net extension for that. It's not part of main akka library, which I think now for good reasons, but there are some extensions. So if you really want at least once delivery, just use Akka, and then you don't need to fall back to Rabbit or Azure Service Bus in between your calls, and it's all inside the Akka system. And I think it's important to mention this step because it shows how often we developers fall into this comfort feeling of using one technology to solve all problems. It's like the old saying that if you just have a hammer, then everything around looks like nails. So we sort of try to use sort of aesthetical reasons, and you should not really apply aesthetical reasons when designing distributed systems. So okay, like everything will be actor based. So it's based on persistent actors. So again, now we need to have some message envelopes because message need to include delivery ID. So each delivery requires confirmation from recipient, and actually this alone breaks very much sort of the nature of the actor model, which is by sort of essence unidirectional messages. Of course, actors can be involved in bidirectional communication. You can also, in major actor system frameworks, you can have like method tell, you can also have method ask. You can ask an actor about something. But I would say it's an anti-pattern. You should build your system, and your system will work in the most efficient way if your messages are unidirectional. And then here we invoke this protocol about this confirmation from recipient. And then we started configuring behavior, and then, okay, we need to configure redelivery burst limit. I mean, how many messages can be redelivered? Then when do we need to send warnings if we have certain unconfirmed delivery attempts? Then what will maximum unconfirmed messages because they take place in memory? So started looking at it. Basically what we were doing, we were trying to design durable queuing system. And then, so after working with durable queues, it looked really like poor man durable queues. So I think it took us something like 2-3 months before we realized that we shouldn't go that path. So don't implement at least one delivery semantics using actors, so just everything runs actors. So there are some proven technology choices, and try to use them if you really need to do it that way. So then eventually we came to version 4, which I believe doesn't only apply to the actor model. So if you design your system without actors, you can also think about something which you can take from this approach. So it's all about fulfillment of desired state. So what we came to realization that it's expressed in this article, nobody needs reliable messaging. This article about web messaging, but I think that the main conclusion also stands for other protocols, for other technologies. So if reliability is important on the business level, do it on the business level. So it's a business, move it to your business concerns. Also, a quote from Pat Helland. So in a system that cannot count received transactions, the management of uncertainty must be implemented in the business logic. So face it there. Instead of like focusing on this micro level, okay, this is my message, I want this to be delivered between these two internal actors. No, think about your business output. This is what needs to be done in the end. So another quote from Pat Helland. So work happens with a sequence of related messages. And this is how it was done centuries ago, and it's how it's done today. So he specifically mentioned that this is something about what was working centuries ago when we didn't have computers, we didn't have distributed systems. So like think about real-world collaboration and try to build your system based on those premises. So we're talking about reliable collaborations with unreliable messages. So let's keep actors as actor message as they are, with at most once delivery guarantee. And let's build surroundings around so we can still end up with a satisfactory result. So what we did then to our system, we changed it. So when we receive incoming requests, we evaluate the desired state of our aggregate root, like what we want, what our intention of this request, what we want to be achieved. And this desired state, it must not only store the state of the aggregate root, sort of natural internal state of aggregate root, it also needs to store information about expected outgoing messages. I'll come back to the Outbox pattern. So we then persist the desired state. So we persist our intention, what we need to change in the system. Then we acknowledge the received messages, the received message. And only then we proceed with request execution with no message delivery guarantee between actors. A couple of words about Outbox pattern. Outbox pattern, it ensures that the application state and the respective domain event, so those who expect events from us, they are consistent, so they're synchronized. And so this is important and sometimes overlooked. Like we send messages to RabbitMQ or Azure Service Bus, and of course those are durable queues. But this durability comes after we successfully placed messages there. So if a power button is pushed right before we send messages there, then we lose this message. So we need to register what needs to be sent and come back to it in the worst case. And this is basically what Outbox pattern does. So you register all the expectation about your communication with outgoing message recipients. So then request execution, it consists of evaluating desired state, evaluating the current state, which we are now in, and then we calculate the work, which is current state minus desired state. And also, we can optimize this operation as much as we want, like if we achieve desired state gradually, like by uploading file after file, we can register what was done, what part of work is done. So next time, if system crashes, we go back to desired state, it's changed. It's current state changed. So the difference will be smaller. It's a pure math. So desired state concept, of course, it's we didn't invent that, but this is something that is used very much in like DevOps-related things, and it's one of the core concepts of Kubernetes, and which makes quite efficient the promotion of Kubernetes services. It also exists in PowerShell. There is a PowerShell desired state configuration. Both of them are similar. They're declarative. You describe what you want to achieve instead of just creating script which tells you 100% of what needs to be done. And then if something crashed, you need to run script all the steps again. No, you don't need. You just describe what you want to achieve, and depending on what was already achieved, you do the rest. So there is an important assumption here. It's idempotency. Of course, if you sort of roll back to previous level, and then you may need to repeat certain operations, but I think the only situation then, if you can't live with idempotency, that you need is exactly once message delivery, and then try to think your system as possible. Sometimes, if you're working with financial systems, you need to have some places where you can't really be idempotent. Those are hard places, but luckily there are only few of them in most of the systems. In our systems, we don't have any such place. In the worst case, we just distribute file twice. So this is just example of how desired state. We describe the content of, I think it's television program. Yeah, there is a program IDs, like part IDs, and there is different files with some information about some metadata of each file. And then there is a current state. We have different origins. So this one's from Akamai, so which says what we have now. So which means that if we need to upload missing files, where there are already some files there, so we only need to apply some deltas. So probably it's easier to illustrate it with such diagram that, okay, we want to publish media set, which consists of a couple of files. So we have the desired state based on that. On the left-hand side, you see the request. Here, the green one, it's a desired state, which is like origin 1 needs 2 files, origin 2 needs 2 files, and this is, remember, Outbox pattern. Okay, notification, media set published, event must be sent. Current state, okay, looks like we already started it, and then something went wrong. So there is a origin 1 which already has 1 file. So we compute related work, which is, okay, send the remaining file to origin 1, 2 files to origin 2, and send notification. So this is what needs to be done. Okay, but actors are reactive. So the actor system is, and the good thing about actors, they're very cheap. They, when they are sleeping, they take no memory. You can have millions of actors in your system, and then as long as they all sleep, you won't notice that system is working. So how do you ensure that like the work is fulfilled? Because we have actor cluster, and then typically for efficiency reasons, like for optimization reasons, each actor is passivated after X minutes of activity. So if actor doesn't get more messages, then it will be deactivated. So what if there are some remaining work, but there are some pending commands and system is stalled, and then actor gets deactivated? So how do we ensure that actor gets its job done? So again, let's think about real world. Let's think about like people being actors. Okay, I don't have like every morning I wake up, I usually think, okay, what do I need to do today? I can have some helper information which shows me, and of course, if I need to be waken up, then there is some kind of reminder. Like today, I knew I have a talk very early at 11:15, so I need to wake up before that. So I had an alarm at my phone. So we changed slightly this processing workflow. So after we relate desired state, we schedule a repeating reminder. So it's some reminder that will periodically send reminders to our actors. Then we persist desired state, and the rest is the same. So we will ensure that if actor falls asleep, if it believes there is not much to do or nothing to do, it will be reminded afterwards. So reminder message may be simply a trigger to wake up the actor, and I think it's rather B. Our first implementation, we thought, okay, we need to come up with some reminders message which would describe exactly what works need to be done. And I think that that's not the right thing to do. Think about that you have like reminders coming to you about in the morning you have this wake up alarm which shows you exactly what needs to be done. Well, you still will need to check up maybe some other things. So you'd better be in charge of your day. So when you wake up, I think you have more robustness if you are self-going. If you can think about, if you can replay your state. Okay, today is 31st of October. Okay, I'm at KanDDDinsky. Okay, I need to remember to do certain things today. Rather than you will need to rely all the time on exact context of what needs to be done. So what we do is all our aggregate roots, all our actors, they're persistent actors, and they are self-going in that respect. So when they replay the state from the event journal, it's called state recovery in Actor world. So they evaluate the current state, the desired state, and evaluate remaining work. So after actor is waken up, it knows, okay, here is state I'm in, here is desired state, and this is remaining work. If remaining work is nothing, so I'm done all my duties. So I cancel repeating reminder. I don't need to be reminded all the time, so I just go to sleep. Maybe I will sleep until next year. And then, no, I'm not done. I keep reminder going, and then I will proceed with the request execution. Main lesson learned when modeling actors' behavior. It's to consider using patterns established in the real world collaboration. So the real world is quite solid, and we can learn a lot from it. And this helps very much to clean up design thinking and the system design flaws which we keep finding in our system. Very often they are indications of we didn't really think about how real processes work. To conclude, so actors use at most once delivery, but this is for good reasons. So let them stay quick and responsive. We don't need to make them implement at least one delivery. That will make communication complicated, and they will make them also much slower. So durable message queues should be used for exactly for the purpose they have, to deliver messages. And if we can, we should acknowledge message delivery as soon as we recorded our intent from that message, and we free the message. We are done with message queue. So then we need to persist our intention, and we need to record the series of changes in our current state which we expect, including the outgoing messages. So then we form this two main parts of our aggregate state, like desired and current state, and then we can start evaluate remaining work based on that. So I think we have time for some questions. That was basically a retrospective of what changes we did through our system during more than 5 years of this being in production. And of course, there was a lot of changes. It went from non-cluster to cluster. Now we're working with implementing support like for OpenTelemetry. But I think the most important sort of single design change which we applied to the system was to forget about guaranteed delivery between actors and focus on fulfillment of desired state of our aggregate routes. So, and this is something, by the way, I think will work also very well, not just in actor world. So if you think about your domain, your entities, you may think about scenarios where this thing also will fit. You can record desired and current state of your aggregates and try implement remaining work based on that. So with that, I thank you for your attention, and I think we have some time for questions.
I do have one.
Sorry?
I do have one.
Yeah, okay.
What if the reminder comes when the work is being done? So like in the actor state, you say the desired state doesn't match, so you calculate this work again and send it out, but it's already being done.
Well, it's not, of course, you may have, it may come, but in this case, you will just get, we only cancel new reminders when there is no remaining work left. Yeah.
So like, let's say uploading the file takes an hour, and I get a reminder that's there help out. I will keep setting the remaining work all the time, so it cannot end up in endless sequence of messaging indicating the work.
Okay. So what if a reminder message comes more often than you have the, let me think. When a reminder message comes, it doesn't tell you, I sort of simplified the situation. It doesn't tell you that you must start everything from scratch. It just reminds you, sort of, basically it says that wakes up. And then it's your tactical decision of what you do from that. you may know at that time, okay, I just started a new upload. So it's just a way to wake up an actor. It's not an instruction, do your work. Yeah, just be aware that you may need to be wake up. Question?
I'm thinking about the desired state of a shopping cart. So I have a request to add something to the cart, and then later on I want to take it out of the cart. So the actor wakes up, sees the desired state for the first goal is add to cart, so it creates that new work list, add this to the cart, and it sends off a message into the queue or whatever, and then another change comes in, and now I want to take it back out of the cart. So it creates a message and sends it off. How do you're going to need to make sure the order of those is consistent, because you get the delete before the add.
Yeah. Yeah, and we need to face this ordering also with our internal messages. For example, we receive transcoding information about transcoded files, and what may happen is that okay, RabbitMQ is down, and then some of the messages they may there was some network problems. Some message went into this retry queue or error queue. I was showing you this retry queue, and then of course if messages is there for 1 hour, then there are some other messages, so it may conflict the original order. So if the order is important, you will need to do some sort of versioning in your messages. So now all these transcoding messages we receive, they have version information. So if we get a message with with earlier version number, we just discard it. So if you have this add item, remove item, and you may in the simplest scenario you just have a timestamp there. If this is good enough for you to rely on that, or you need to have explicit version info. So you need to take care of ordering, yes.
So you need some source of sequence that's consistent across all the actors. So if they create a new state, they could get a sequence ID?
Yeah. In our situation, in most of the cases, timestamp is sufficient, but there are some scenarios where it's not. Question?
I'm wondering the calculation of the desired state. But how is this different to just persisting the command that's coming in? So I could just persist the command and do some transactional handling until I got to the outbox patterns or the events. And in case of error, everything will be rolled back. So is there some difference to just storing the incoming command or persisting the incoming command?
Well, desired state is not just coming command, because command may not express the whole desired state. For example, we have files, we have also subtitle information, and subtitle information come from a different department. So we may get a message about transcoded files, like MP4 files, and then there is a message coming about, okay, this is subtitles in English. So then desired state, it's not just this apply subtitle, add subtitles command. The desired state, it's a desired content of your sort of aggregate root, which will be consisting of X files plus subtitle information. So so the command may add to the desired state, but of course you build, when you replay incoming commands, you build your desired state. So it's basically a snapshot of sort of latest intent of how you would like to see aggregate root, but it's not just single command, can be much less than that. But it's very close to that. Of course, you build from commands and you form this desired state.
So we have one last question, and then you can answer all the questions on the way. We need to hurry up.
You mentioned that, for me, it was the main thing I took away, that you can move your guarantees into the business. So can you give us an example perhaps of, you also said that the real world is solid. Can you give us an example of a time where you've moved those guarantees into the business, and how did the real world then react as a consequence of what you did, as in like your system, how did it change?
Well, we have several clients of our system. One of them is those who publish news clips, and they always send us just exact instruction of what needs to be done. So it's very easy to fall into just okay, let's execute just each particular command, but and it's sort of in the first version we were like not acknowledging anything until each command was completed, and then what we did we later that we record them. Then, as I also was explaining for the first previous question, we based a cumulative state of the news clip which we want to have, and so this forms our desired state, and this is sort of business concern. We have a news clip which consists of these files, so each particular command just contributes to it. We no longer execute one and single command, and then we calculate remaining work. Because of the fact that we don't always execute every command we receive, we can optimize it. So if we had a problem with a network and then we need to restart, and it's expensive to restart, re-upload files if it's a large files. So we always start at that sort of latest bookmark, which is desired state as we recorded, and this is current state which we have. So in this case, the business is what we want to have in production, what we have now, and then this is often small difference which needs to be done. So it's rather than blindly following each and every command. So perhaps I could think about some more interesting example, but I'm sort of very locked to my domain right now. I can think maybe if I come.
Sorry.
Okay, we can.
You can continue the talk on the hallway.
So again, thank you very much for coming, and enjoy the rest of the conference.